For years, the path to more capable AI seemed, pretty simple. Just add more data, more parameters, and throw more compute at the problem. But as we're looking ahead, the frontier models are making this really critical architectural pivot away from that brute force thinking. So today, we're going to explore the elegant solution that's defining this next generation of AI, Dynamic Compute Allocation.
So here's how we'll break it down. We'll kick things off by unpacking a really counterintuitive problem that I'm calling the planning paradox. From there, we'll look at how we found the sweet spot, the Goldilocks zone, and how that leads to an elegant architectural solution, the intelligent router, which is going to move us completely beyond the whole era of manually switching between different models.
All right, let's start with a mystery that's been bugging system architects for a bit. For a long time, the dominant agentic frameworks, things like React, were built on this really intuitive idea. To solve a hard problem, an AI should stop and think before every single action. Makes sense, right? But it turns out this always plan strategy is actually deeply flawed.
And this leads us to a genuine paradox. Why is it that forcing an AI to constantly replan and basically overthink a problem actually makes its performance worse, especially on the big, long-horizon tasks we really care about? The answer is surprisingly elegant, and it has huge implications for how we design these systems.
As you can see, the research shows that both extremes are basically just failure modes. The always planning strategy, it leads to this tangled mess of behavioral instability and super wasteful backtracking as the model just constantly changes its mind. But on the other hand, the never planning strategy is just as bad. You end up with this erratic, impulsive behavior that just can't handle complex goals. So, yeah, neither approach works.
So if the extremes don't work, there has to be a sweet spot in the middle, right? This is where the research gets really exciting, because it uncovers a Goldilocks zone by actually quantifying the hidden costs and the benefits of all this agentic planning. Let's dig into the science here. This quote from the paper, "Learning When to Plan," just nails it. For any given task, there is an optimal, sort of intermediate frequency for planning. It's not about thinking more, it's about thinking at the right time. And this discovery, this is the key to unlocking way more efficient and effective agents. So the really crucial thing to understand is why overthinking fails. The researchers identified this conceptual cost they call C noise, or instability cost. And this is basically the performance hit you take from too much replanning. See, when an agent is constantly reevaluating its strategy with imperfect plans, it introduces noise into its own behavior. It starts to oscillate between goals or even abandon perfectly good paths. It basically gives it self-analysis paralysis.
And this table really just drives the point home. Take a look at the dynamic planning strategy. That's our Goldilocks approach. It achieves the highest performance on these complex, long-horizon tasks, but it does it with an optimized computational cost. It spends its thinking budget strategically, only planning when the benefit actually outweighs that instability cost we just talked about. It's simply the most effective and efficient way forward.
So how do we take this Goldilocks principle and actually build it into the architecture of these new frontier models? Well, it's not just some clever prompting trick. It's being baked directly into the system through a concept called Dynamic Compute Allocation.
Here's the high-level flow. When a query comes in, it doesn't just get sent to one giant monolithic model anymore. Instead, a lightweight, super-fast router first analyzes the query. Based on that analysis, it picks the best model or reasoning path for the job, and only then is the task executed. Think of it like an intelligent traffic cop for compute.
And the key user benefit here is that this solves the growing problem of what some people call LLM fatigue. We no longer have to manually decide if a task needs a fast, cheap model or a slow, powerful one. The system makes that decision for us, instantly and completely behind the scenes.
Okay, to make this really concrete, let's peek inside the brain of a system that's reportedly implementing this perfectly, OpenAI's next big model. The core of its architecture is this intelligent, real-time router that basically acts as the system's central nervous system.
So how does this router decide where to send your query? Well, it's looking at several signals on the fly. First, it assesses the query's complexity. Is this a simple question or a multi-step reasoning problem? Second, it checks for tool needs. Does it need to call a code interpreter or browse the web? And finally, and this is cool, it listens for explicit user intent. If you literally say, "Think hard about this," the router takes that as a direct command to fire up the big guns.
And based on those criteria, the router is choosing between at least two primary models. For most of your queries, it's going to default to the main model, a fast, efficient model that's perfect for chat and simple tasks. But When that router detects high complexity, or you explicitly ask for deep thought, it invokes the thinking model, a much more computationally expensive beast that's built for deep, chain-of-thought style reasoning. The system is dynamically switching between speed and power all on its own. Okay, so let's zoom out a bit and think about the broader impact here. This shift towards adaptive AI that allocates its own compute, it's more than just a clever engineering trick. It fundamentally changes how we design and even how we interact with these systems.
So what does this new architecture really unlock for us? For system architects, the takeaways are huge. First off, it ends that manual selection headache, which is a massive win for user experience. It optimizes compute costs by only using that expensive reasoning when it's absolutely necessary. It also directly enables the Goldilocks principle we talked about for much more effective agents, and it helps evolve these systems from just chatbots into truly autonomous digital workers. Ultimately, this is a critical step toward more scalable and steerable AI.
This whole architecture is just a powerful solution to efficient resource allocation. But it does leave us with a new, and I think critical question. Once the model itself decides how much to think, once compute literally allocates itself, what becomes the next architectural bottleneck? What's the new problem we have to solve?